Let me introduce very interesting topic, room acoustics. Okay. Room. What is a room? What is a room? There are many rooms, but we are talking about room with regard to first what? Enclosure? Enclosed space. That's a very nice comment. Enclosed space. Okay. What do you mean by enclosed? In terms of scientific terminology or engineering terminology, what do you mean by enclosed? Enclosed. Okay. What we have been studying, acoustics, we have been trying to understand the physical behavior, physical things of acoustics in terms of what? What measure we usually use to understand fundamental concept of acoustics? Huh? Relative scale, that's very good. We see the scale, for example, KL, that means we see the length scale with respect to wavelengths of interest. And, of course, frequency. Okay. And I announced that the possible name of my future book in English version would be what? Sound and impedance. Sound and impedance. We always try to understand the behavior of a sound in terms of impedance. Right? Scattering problem. Incident wave there is, and due to the presence of a scatterer, or we can say due to the presence of impedance discontinuity in space, there will be some reflection like we have reflection and transmission when we have a flat surface of discontinuity. That is also impedance discontinuity in space. Right? So enclosure, enclosed means enclosed by what? Impedance discontinuity. Okay, now we can regard the room is a enclosed by the wall, so the wall means impedance discontinuity. For the scattering problem, incident discontinuity was regarded as the outside of the obstacles, but now this impedance mismatch is now inside of the enclosure. That's the difference. So now we are considering how the sound waves will propagate inside of the volume that is enclosed by the surface of this continuity. Okay? What does it mean by space? Does this space is a very large space or small space compared with wavelengths of interest? So in this case, we see that typical length of the room is very large compared with the wavelengths of interest. Okay? So this room is very large compared with what I am making, what I am producing sound now. 1 kilohertz, this wavelength. This room is much, much larger than 34 centimeter wavelengths. It's very large now. Okay, the room is large. And I am generating sound over here, for instance. And what's going to happen? And so we'll go over there and hit, and hit, and hit, and hit. How fast? 343 meters per second. So when I, and then, right? And what's going to happen inside? The energy over here, at any point, I can argue that would be, I mean, if I take energy over here, and compare with the energy over here, then the energy would be quite similar, right? This kind of field, we call it diffuse field. Okay? The other extreme case compared with diffuse field would be what? The sound that can be made by no reflection. This field is made by many reflection, right? But if there is no refraction, then we call it direct. In between, we call it reverberant. So in direct sound field, the sound pressure will decrease by 6 dB per octave of the distance, right? Because it's spread out. In diffuse sound field, sound pressure is constant. What do you hear? 태식, 태웅, so 태석, sorry, 태석. What here would be same as what he hear, because this room is produced. The sound will be produced by many refraction.